Myself, Dr. Vinod.E.Madhavan. Let me start my talk. Basically, it's regarding emerging solar technologies. You must have heard about lot about the currently existing solar panels, which is basically silicon based. Now we are going to discuss something more beyond your knowledge that there are some other research level solar cells are on make. You will be able to see some lights in this direction. And before begin, I would like to thank Dr. Hamza Anchmukil and Dr. Ahmad Fayaz, and also all the management and staff of Marcus Knowledge City for inviting me here. So basically, I understand this is a business investment meet, and you must have seen a lot of business opportunities. But in the coming decades also will be having a lot of new opportunities which you can't see at present, mainly because it's all in making. At some stage you will be able to see whatever you are seeing at present basically is somebody's effort at least few years before. My collaborators, where I worked mainly in the area of solar cells. This include, KIRI team. KIRI is nothing but Qatar Environmental and Energy Research Institute. We have worked there. Our collaborators are shown in the first left photo. And on the right side, you will see an EPFL team. EPFL is nothing but Ecole Polytechnique. It's from Switzerland. We have worked there. And also, he is my PhD advisor, Professor Shangundi from Indian Institute of Science, Bangalore. And also you see HZB, which is Helmholtz-Zentrum, Berlin, in Germany. So these are the places where we mainly worked on the research of solar cells. And I think the slide transition have an issue. Yeah. So we will, in the today's talk, we will talk about different kind of solar cells that we created, we invented, and how this is going to change, the way that you will see in the coming decades will be explained. What you see on the right side is basically the solar cell that we prepare. The dimension of that solar cell is around 2.5 centimeter, 1.5 centimeter. So in a lab scale, you don't make a very big solar panel that what you see. You basically make a very small scale cell, and you will try to measure the efficiency of that. The solar panel has some efficiency in it, right? That is around 18% to 20 or 22%. So basically, all these solar panels are made up of silicon. But now we are bringing a new material that is called perovskite material. This material can, revolutionize the solar cell industry because we need very less material with respect to the silicon solar cell. We need very less material in order to make a high efficiency solar cell for the purpose. And what you see here is basically, a thin film solar cell, and that can be even line your shirt. So the material that we use for solar cell is basically an ink or a dye. That dye, if you use it effectively, you can print it on your shirt or onto any surfaces from where you can generate electricity. So that's how the effect is going to come. And the same solar cell, if you integrate with the existing silicon solar cell, you will be able to see the efficiency is increasing much higher. It's showing around 29.52% of efficiency is achievable if you make it a tandem configuration. I will soon discuss with you what is a tandem solar cell configuration. And very recently, Helmholtz-Zentrum, Berlin explained and demonstrated in 19 December 2022 that they have achieved an efficiency around 32.5% of efficiency in a solar cell. These are all very, very great innovations in very recent days. We'll be able to say. So let's begin basically, because all our discussion is basically based on the green technology. And what is this green technology? Where this term coming from? So the next slide, please. When we say green technology, that works. No, maybe you will have to. Yeah. So green technology is basically an umbrella term that explains a lot of different areas added together. There is a research of material science. There is a research of all green vegetables. All different areas are encompassed to make a green technology. The basic idea of green technology is to reduce the human footprint. Actually, when you know about the human footprint, what does it mean? Reduce the human intervention into the environment. We all know that everyone releases carbon dioxide. How do we reduce this? We can reduce it by several ways. Some of the ways we will try to explain here. And not just that. That gives you a lot of opportunities for investment, because all our new green technologies bringing a lot of innovation as well as investment opportunities, as you can see here. All socially responsible innovators will try to bring green energy, and that brings a lot of investments. As you can see, the next slide. The next slide, please. Next one. Yeah. So the basic idea is to have avoid the negative effect on our environment. The next slide, please. So how do we achieve this? The first method is called alternative energy. What is this alternative energy basically means? Alternative energy is nothing but renewable energy. You know, the renewable energy is what we are talking today. All the solar panels, all solar energy, all the wind power, all the, all those terms comes under renewable energy. And the next option is electrical vehicle. When you bring electrical vehicle into the market, you will be able to reduce your carbon emissions. When you reduce the carbon emission, again you are bringing more green technology into practice. So, yes. And in the case of sustainable agriculture, instead of using, yeah. In the case of sustainable agriculture, that you see, meat substitutes are now discovered. I mean, carbon emissions are released in the process of agriculture. So you can do sustainable agriculture also, and that will give you a lot of improvements. And there are a lot of solar panels, but at some stage, you will see that this solar panel will start generating waste, because the panel that you install today, after 25 years, that will not be no longer a working solar panel. So that will start generating a lot of waste materials. So you will have to recycle. Why? Because the precious element that we use in a solar panel is basically silicon. The silicon is coming from nothing but from the sand. But then you also use some silver lining, copper lining, indium, etc. So those elements, what you will do, you will have to preserve it, because at some stage you will use it. All the material you use, then you don't have any more materials for your further usage. In that case, what you will do, you will be able to use it in a better way by recycling it. How do you recycle it? In order to recycle it, there are many opportunities are lying there. people started working on it. People starting, shredding the panels, cutting it, and separating its contents. All the aluminum panel, all the silicon, everything you can separate by different chemical or physical methods. And people are working heavily on carbon capture because the carbon that we are emitting, either by human or by our vehicle or by any other means, need to be captured back, because that goes to the ambience, and what it happens, it starts generating heat. This heat is a problem. Actually, heat will create a kind of global warming, and in order to avoid that, what do you have to do? You still have to work on carbon capture. Such kind of research is also going on now. So all these things, you need some alternatives. These alternatives means opportunity. How do you make opportunity? For example, we say that one time use plastic should be avoided, but then you need an alternative like a paper bag or something. We don't have plenty of paper bags now. So you see, there is an opportunity. Similarly, a lot of opportunities come from the green technology, which is our case. But you also remember, all these green technologies are not foolproof. A lot of issues also will rise. For example, if you want to use an electric vehicle, you need a lithium-ion battery. A lithium-ion battery means what? You need a lot of lithium, right? In order to have lithium, you will have to mine it. But then plenty of lithium will also, you cannot use it indefinitely. At some stage, you will have to stop it and start reusing it, right? Similarly, all technologies come with some compromise. Then you will have to have a judicious compromise on technological development, and at the same time, you try to use it in a very, very viable way. So that's how we say that careful accounting is required. So the cheapest form of green energy is nothing but solar energy. I'm going to tell you some of the green, green energy alternative, which is a solar cell, a latest type of solar cell that we created in our lab, and how much efficiency that we got. It's sometime, it was one of the highest efficiency that is reported. And so now you have an idea about what is a green technology, which is an umbrella term that describes reduced human impacts on natural environment. Whatever you do, if you are able to achieve that by a method, then it is a green technology, and it is having lot of scientific research involved, which includes atmospheric science, energy science, agriculture, material science, hydrology, etc. So now let's try to see what are these renewable energy. Renewable energy is simply not solar. You also know that there is a geothermal energy. What is a geothermal energy? The earth consists of lot of heated lava inside. When it comes out, lot of energy is emitted out. That has some energy in it. Similarly, bioenergy from biofuels can be created. So there is a biofuels, there is geothermal energy, and hydropower from the dam that we generate electricity. And similarly, marine energy, the waves can generate energy. So these are renewable energy, and you will be able to use it freely, but at the same time using different technologies very effectively. So this renewable energy will benefit you because you will have increased energy independence. You don't need to depend upon the fossil fuels. The fossil fuels is going to end at one point, and it is also creating a lot of carbon emissions. But renewable energies are not, though there is something that has to be taken care. So in the case of renewable energy, we started developing these different kind of solar cell technologies that started with inorganic wafer-based method, which is a silicon one that you can see in the first table. So silicon technology started as a first generation solar cell technology. It's a very, very old technology now, but right now it is in the market because whatever you do research now will be showing into your market after 20, 30 years. So whatever we do now will be shown maybe after few years. It's not immediately available because technology need a lot of refinement and optimization. And there is a second generation which is inorganic thin film, which is also currently in the market. You can check different websites. There is called cadmium telluride material. So now we are talking about materials. In the beginning we said silicon. That is the first generation. And the second generation we are coming to cadmium telluride. So another material that we discovered which can again produce renewable energy or solar energy. And I also want to tell you, we all know about the solar cell panel will give you electricity, but I wanted to take you to the basics of solar cell technology a little bit. So you will be able to understand how this energy is generated from that tiny piece of material, which we will do soon. And there is a third class that's called third generation, which includes organic thin film and organic inorganic hybrid. And this organic inorganic hybrid is where I mostly focus on, and I will be able to show you some of the slides that we basically did actually. So you know that when you see a solar cell is basically not just a sheet of paper, right? It has several layers in it. What are these layers? That has a top layer, which is a glass. What do you do in a glass? The glass, why we should not keep any opaque substrate. We need to have a transparent substrate because sunlight should fall onto the underneath material. So you have a glass that will allow you high transmission, and then you have an aluminum frame in it. And also inside, when you go very deeper, you will be able to see there is a solar cell. That's a solar cell layer actually, as you can see here. This is your solar cell layer. Now, again, there is below that there is a plastic layer in it, which is called a EVA sheet. That's a polymer layer. And there is a back sheet, which is also another polymer layer, which is also called PVF or PVDF. And at the end, you will be able to see two lines are connecting out from the solar panel and put at some place called a junction, which is called a junction box. Then you will be using it for different purposes. So there are several layers here. But then the main layer is the solar cell, which is in the one which I showed you. So that layer is the solar cell. Remaining things are protection layers or supporting layers. So what is basically happening there? When sunlight hitting on a silicon layer, the silicon layers are not so innocent layers. A lot of engineering is done on that silicon layer. You must have studied, if you have learned about semiconducting physics in your intermediate or +2, that basically there are silicon consists of P-type and N-type. So a silicon means a silicon material, but then the material consists of silicon atoms, and silicon atom basically consists of lot of electrons in it, right? You must have learned about that orbiting electrons around the central nucleus of a. So there are many silicon atoms put together, and you make it either P-type or N-type. All electronic industry needs semiconductor to survive. Whatever you see, including all electronic devices need semiconductor material. And what we are dealing with in a solar cell is also a semiconducting material called silicon. How will you make it an N-type or P-type? That's a very good question to think, because if you have a N-type or P-type, then only a solar cell will work. So you will basically see that there is an N-type layer, there is a P-type layer, and then you will have a lot of lining, like this blue lining will be there, which is the electrical contacts that will take out these charges from the N-type or P-type silicon. So when sunlight hits, there is basically an electron and charge carrier generation is there. So this is also not very, simple way of thinking. You will have to see little bit in detail. For example, so the next slide, please. So a solar cell look like this in a circuit diagram, something like this. What do you see? You will have to see a P side here. That's the P side of your solar cell, and there is an N side, and the sunlight will hit onto it, and there will be an electron and holes. Both are the charge carriers here. That will be generated. It will be going through your external circuit. Microampere represents a current, and voltage V represents a voltage. So this is how a solar cell is represented in an electrical circuit. So what is basically happening? Sunlight is coming and electrical charge is generated. So when all these atoms are mixed together, then there is something called band gap. That's an important concept in solar cell. The charge carriers will be creating one valence band, one conduction band, and when the sunlight hits onto this P side and N side. Now P side is what? A P-type silicon, and N side is what? An N-type silicon. Basically, P-type and N-type are made with doping with some elements. That elements are shown here. P-type is basically made up of boron, aluminum, gallium, indium, doped into silicon. And N-type is made basically with phosphorus, arsenic, antimony, bismuth, and lithium, doped into silicon. So the same silicon you make either P side or N side by doping with different elements, so that there will be electrons as charge carriers or holes as charge carriers. So what do you do basically by the charge carriers here? You'll be able to allow them to generate more charge carriers, and it will go to the conduction band from the valence band, and this process will continuously happen, and that will generate electricity in the external circuit. So what happens? Three processes are happening in a solar cell. Basically, the first one is generating electron hole pairs. That's the generation part when the sunlight hits, and there is separation of electrons and holes. These electrons and holes generated inside the material should go to your external circuit, either in the top electrode or in the bottom electrode. So there should be a separation, and there should be a third process called collection. This is collected and sent to the external circuit. So this is how the current and voltage of a solar cell will look like. When you plot it in a graph, you will have an voltage curve, and there will be a current curve. So this will be your voltage and current generated inside a solar cell. So why I said all this? Because in order to create a solar panel, you need to have some special type of material that has all these properties. It should have a band gap, ideal band gap, which is in the range of 1 to 1.8 eV, and there should be high optical absorption. When sunlight hit on a material, all the sunlight should be absorbed by the material, and there should be good electrical conductivity. All the charge carriers that is generated inside a solar cell material should go to both electrodes, from the material to the electrodes, and the raw material should be plenty available, and the cost should be low. So all these criteria is satisfied, then only your solar cell panel will work. So you will, when you do research, you will have to look all these parameters one by one to meet all the required things. So you know that solar cell has many applications which you are all aware of it. That anyway, I don't need to explain to you. It's used in satellites. It's used in all our home purposes, all calculators, all small appliances. We use it. It's a pollution-free energy basically. However, it's not very free. There is a cost involved. Even though the sunlight is free, in order to make the technology working, you need to put a cost in it. So it's not very cheaper. And obviously the sunlight is the most important factor here. You need to have a good, sunlight coming onto your panel, uh, so that you will be able to get a very good efficiency. So when you have a solar radiation which is coming into your material, you will have to see, the sunlight which is coming onto your material is not very simple thing actually. How much solar energy is hitting onto your panel. If it is 100%, how much it will be converted into electricity will be your efficiency of the panel. For example, I have 100% of sunlight coming into my panel, and I see that around 10% of that energy I convert into electricity, then I can say my panel has 10% of efficiency. It is also possible, some cases, some material is so good so that I will be able to convert 20% of the material into electricity. Then it is a 20% efficient panel. Most of the panel that is coming into the market now, right now, is in the range of 18 to 22%. All the silicon panel that is coming. And there are a lot of technical information that we need to discuss, what kind of panels are coming. There are a lot of technologies, different layers, or each layer is made with a lot of light reflection, those kind of things, in order to make it more efficient, which we are not going to detail. So I showed you this sunlight at the top of the atmosphere will not be what is available below and close to the earth, which is the red part. The red part will be only available to us. From that, we will be able to convert required sunlight, required energy. So I'm not going to go into the details here, but what I wanted to show you is, this sunlight which is coming into the earth, all of that energy we cannot use in a solar panel. Only part of that is used by even silicon technology. So the silicon technology, for example, this is our visible light, from here to here, this is our visible light. And our silicon panel is the blue part. This much energy it can absorb when the sunlight is coming into that material. So remaining, all remaining energy is going to be waste. So if you are a researcher, you will try to do what? You will try to absorb this part of energy also into your solar cell, so that it will be more efficient. And recently a material is discovered which is called perovskite material that can absorb, exactly that UV visible light, the visible light, that what we see here. The entire that light can be absorbed by that material more efficiently than silicon. So this is much higher power output than silicon, which is going to be the next generation solar cell. So probably I'll skip many of these slides because we have time limitation. So for a single junction solar cell, the maximum efficiency is possible by considering many things is 33%, but we are no longer close to that. As I said, we are only up to some 22%. We can go up to 33%, but this still need a lot of optimization, and people are working to optimize that part, and people achieved up to, as I told you, around 32% when they use a tandem configuration. So I'll just quickly show you some of the work that we did. So if you have time, sometime, just search this graph. It's called, NREL plot. That shows all the existing solar cell technologies currently on research, not available on the market. How this efficiency is, increasing day by day or year by year. So the cell efficiency is shown in the y-axis, and x-axis is years. So in 2022, different technologies are shown here. Those technologies and how much is the efficiency that we are trying to get with different methods are shown here. So it shows up to 47% if you use a concentrated sunlight, because usually the sunlight that we use is one sun. We call it one sun because it's around 1000 milliwatt per centimeter square. But now when you use a concentrated sunlight, you will be able to reflect one sunlight through different mirrors into one point. So you will be able to create two sun or three sunlights, so that you will be able to generate even much more than the 33% that we discussed previously. We can exploit that condition limitations and go to the higher level of thing. And what I wanted to say, in research, different things are ongoing, and one of the technologies is called perovskite solar cell. It's an amazing material that has it has a broad absorption spectrum. All the charges that is generated inside the solar cell, electron and holes, will be separated quickly from the material into the external circuit. So there is long carrier separation lifetime, etc., etc. And so this is how a lab scale solar cell is made. Basically, you will start with a glass plate with an FTO substrate in the top, the blue one, and you will deposit a compact TiO2 layer on top of it. And then you will try to deposit another TiO2 layer. So these layers are deposited with the thin film deposition methods. So various layers are deposited. Then you will deposit a perovskite absorber layer, then a whole transport layer. Then your solar cell is made. You start with a glass plate in the lab, but at the end you will generate something like this. These are gold electrodes on top. So then this will show you all the efficiency that you want to see in a solar cell. And when it is really stable and it is working for years, then you will be able to see that is already in market, and you will be able to lot of economic possibilities are coming. So these are the different layers and its details. I am not going to discuss it. And we found that this lab scale solar cell was able to show you 1 year stability in the beginning, which is not a small thing. It's already published in international journal. Those kind of results are shown here. And there is another material called ZZTS solar cell, which is copper, zinc, tin sulfide. So people are working on ZZTS material in order to improve the, in order to find future generation solar cells. And people are also working on tandem solar cell, combining two solar cells together. One solar cell will absorb part of sunlight, and remaining light will be going into the next solar cell, and both of them you add together, you will get a higher efficiency. That's how we were able to go up to 32% efficiency. So people are also working on, so if you put more junctions, you will be able to go up to 53, 4 junctions, 53% of efficiency. It's possible. So this is all done with the research efforts. And there is amorphous silicon panel, that what we see is a bulk silicon. You can also make a film out of it, which is an amorphous silicon, thin film solar cell. People are also working on it. It's already in market actually. And CIGS solar cell, copper, indium, gallium sulfide. These are another material people are working on to bring into market. And I would like to, and there is organic photovoltaic devices. And even though we are doing a lot of things, these solar cells market is very huge in the future. In future you will see that a lot of money is invested in this area, not only simply silicon solar cell. All thin film solar cell will come into different devices, as you can see in the coming decades. So a lot of money is invested there, and people are also integrating it with buildings. As you can see there, the building is having a lot of different colored materials that will allow light to pass into that, and at the same time it will also look beautiful. Yeah. So that you'll be able to do these kind of things. So in the final part, we will be able to say uh, solar testing is one opportunity. All the panels can be tested. That will give a lot of revenue. Companies can think about that. And the recycling is also a big area that is identified by many experts so that people can generate revenue out of it. And finally, you can also test the solar panel efficiency in order to find out uh, how it is performing. That is a very big data. People will try to buy it. And with that, we have a long way to go in order to, compete with the fuels, other fuels, fossil fuels. So with that, I would like to uh, show you the acknowledgements. These are my colleagues from NITC and with Dr. Ivan from EPFL and some colleagues from KIRI. And I thank Department of Physics, IAC. And if you want to ask anything, I'll be available, but there is a time limitation. I don't know how they are going to manage. Thank you for your attention.